Hi students, welcome to this video in which we're going to discuss the topic of lecture 13, which is galaxies and our Milky Way galaxy. So in other words, we'll talk about our Milky Way galaxy, but also galaxies in general. First of all, let's define what a galaxy is. Actually, I defined it previously in this course, as you may recall, but let's recap. Let's review what the idea of a galaxy is. A galaxy is a large collection of stars, and by large we mean on the order of hundreds of billions of stars, typically, although some galaxies are smaller than that. Galaxies contain other things as well. If you were to look at a galaxy through a telescope, you would notice stars in particular, since stars shine. But there's other stuff you would notice if you looked more carefully. There are gas and dust clouds that are bound together by gravity, and there are other smaller bodies contained within the galaxy that would be harder to see. I should also say, and this is a little preview of what we will talk about toward the end of this lecture, that we believe that at the center of every major galaxy is a supermassive black hole. So I should include that in the constituents of galaxies. Our galaxy is called the Milky Way, and I want to first start off by talking about something that's a little bit tangential to the course, and that is the descriptor barred. Sometimes you will see galaxies described as being barred or non-barred. The Milky Way galaxy is what's called a spiral galaxy, which means that it looks like a disk, a rotating disk, a little bit like the solar system, just in terms of the geometry. But the spiral part means that it has spiral arms. It has arms that move outward from the center, and the Milky Way galaxy rotates around the center. And the barred part refers to galaxies that have a central region that looks like a bar. There's disagreement about whether the Milky Way galaxy is barred or not. But I just wanted to get this out of the way, since if you look up the Milky Way galaxy, you'll notice there's somewhat of a discrepancy about this. So some galaxies are barred, but that's mostly tangential to the topic here. I'll just leave the barred part aside. Let's talk about the size of the Milky Way. The Milky Way is about 100,000 light years across, and it's about 1,000 light years thick. This tells you that it's much wider than it is thick. Which is related to the fact that it looks like a disk if you were to just look at the overall geometry. Remember that a light year is a unit of distance, not time, and it's the amount of distance that light travels in 1 year in a straight line in vacuum. In other words, if you wanted to cross the Milky Way galaxy, let's say at the speed of light, you would have to travel so quickly that you would go, that you could go around the equator of the Earth 7 times in 1 second. That's the speed of light. If you could travel so fast that you could go around the equator of the Earth 7 times in 1 second, but instead travel at that distance in a straight line across the galaxy from one end to the other, it would take you 100,000 years to cross the galaxy. It would take you about 1,000 years to traverse the thickness of the galaxy. However, that is a rough estimate because the galaxy doesn't have a constant thickness. A galaxy has a disk, as I alluded to earlier, but it also has a galactic bulge in the center, which is a relatively very dense area with a lot of stars that has a lot of radiation, emits tons of light, which is radiation. And the galactic bulge is about 3,000 light years thick. Here is a picture or 2 pictures of our Milky Way galaxy. We don't have any pictures of the Milky Way galaxy from outside the galaxy. So you cannot find a picture of the entirety of the galaxy because we live within it, and we cannot send any craft beyond the galaxy. It's too far, essentially. It would take too long for a craft to get there. In any case, this top picture here is from Earth. where you can see the center of the Milky Way galaxy and you can see part of the disk. And the bottom picture here is actually an artist's conception, which depicts the galactic disk, the galactic center, and the galactic bulge. I should probably draw on this. Okay, here's the galactic bulge, which, as I mentioned, is roughly 3 times thicker than the disk. Here is Earth. One question that you might be asking yourself is, where are we within the galaxy? The answer is that we're about 2/3 of the way out from the center, roughly 25,000 light years out from the center. Excuse me while I just erase this so I don't mar my own slides. This is another picture of the Milky Way galaxy that from Earth, obviously, that I wanted to show you just because I think it's a really beautiful picture. Here is the first picture I'm going to show you in this lecture of another galaxy. This is a picture of a whole galaxy from the outside. This is our closest galactic neighbor, or more specifically, our closest spiral galactic neighbor. Remember I mentioned that the Milky Way galaxy is a spiral galaxy, which means it has a disc-like shape and then spiral arms which come out from the galactic center. It's a little bit hard to see the arms here because of the orientation of this picture. So I'll leave the spiral arm part for a little bit later, but here I just want to point out several of the major components of a spiral galaxy. We have the galactic bulge. I'm repeating myself a little bit here, but this is just an example of what a galactic bulge looks like in another galaxy. Then we have the galactic disk, once again similar to the Milky Way galaxy. And something I didn't mention is that there's a massive galactic halo surrounding the galaxy, which is mostly invisible. The galactic halo is everything around the galaxy, basically, in this picture. There's a background in this picture. All of these stars, well, actually they're galaxies, really, although they're, of course, made of stars. But nonetheless, everything in the background is not part of the Andromeda Galaxy. But surrounding the Andromeda Galaxy in this picture is this essentially invisible halo. There's some visible matter in the halo, but the halo is generally made out of dark matter. And we will talk about dark matter a little bit later in this course. I'm going to leave that as an open question as to what exactly dark matter is for a little bit later. Let's talk about the motion of our galaxy. I told you that our galaxy is a disk that's rotating around. It's rotating around its center at the place where we're located, I should say. It's rotating around its center at about 250 kilometers per second, which is about 500,000 miles per hour. However, the galaxy is so huge that our solar system takes about 220 million years to complete one revolution, even traveling at about 500,000 miles per hour. In addition, the Milky Way galaxy is moving with respect to the other galaxies. By the way, there's about 100 billion, on the order of 100 billion, probably more, galaxies in the universe. The Milky Way galaxy is moving away from, and therefore other galaxies are moving away from the Milky Way at tremendous speeds. This is true of virtually all galaxies in the universe. All galaxies are moving away from us, and we're moving away from virtually all galaxies. The Andromeda Galaxy is a special case because of local gravitational forces. The Andromeda Galaxy is moving toward us, and vice versa. The Milky Way galaxy and, our galaxy, the Milky Way, and the Andromeda Galaxy will therefore collide at some point in the future. But this is relatively rare. Virtually all the galaxies are moving away. I mentioned to you that the Milky Way galaxy is very large. It's 100,000 light years across. This is far larger than the solar system. It's a little bit difficult to visualize what 100,000 light years means, however. In fact, the number itself probably doesn't mean anything to you, so you're probably not visualizing it at all. Let's see if we can come up with some kind of analogy to visualize it. Let's ask the question, how large is the Milky Way galaxy compared to the size of the sun? That's the first question here. Suppose that the Milky Way galaxy were the size of the continental United States. Therefore, we're going to build, this is a thought experiment, we can't do this in real life, but we're going to build a map which is literally the size of the entire country, well, at least the continental United States. We're excluding here Alaska and Hawaii. Sorry to be exclusionary, but this analogy only works if we just take the continental United States, or if you'd like, you can take Canada. So I build this map, which is the size of Canada, or the continental US. How large would the sun be on this map? So this is literally a map that covers the entire continental United States from east to west. The sun would be the size of the period at the end of this sentence. If your contribution to this map was to denote where the sun is and to the right scale, to the right size, you would literally go up to the right part of the map and do this. In fact, that's a terrible depiction, but something like that. We could ask another question, which is related, which is how many suns would we have to place from end to end so that they traverse the entire Milky Way galaxy? Suppose, in other words, that this is the Milky Way galaxy. We want to, and now let's say it's not a map, it's literally the galaxy. And we want to take the sun and replicate it. We're going to copy and paste. Once again, this is impossible, but as a thought experiment, suppose we could copy and paste the sun. I don't have a yellow marker. I'm sorry. I'm going to use a red pen here. Forgive me, but this is the sun. And we're going to replicate the sun over and over again as many times as we like. And we're going to place these suns end to end to form a line. This is a line at the bank or whatever, right? But instead of people, it's a line of suns. How many would you have to place end to end to traverse the entire Milky Way galaxy? This is a reasonably straightforward calculation to do. I did it for the slide, and the answer is 680 billion. 680 billion is a large number. It is difficult to comprehend exactly how large this number is. So, in order to do so, let's actually visualize it in a similar way. Let's say we took 680 billion US $1 bills and we stacked them on the surface of the Earth. How far would they reach? So you're going to start from the grass somewhere, go to a park, and or it doesn't matter, the street if you like, and you're going to start stacking $1 bills until you get to 680 billion. If you did that, once again, this is impossible, but the top of the stack would reach a quarter of the way to the moon. This M should be capitalized, sorry, the moon, meaning Earth's moon. This is how large 680 billion is. And that's how many suns you would have to place end to end to traverse the entire galaxy. This represents my best attempt to explain in conceptual terms how large the Milky Way galaxy is. Bear in mind that the Milky Way galaxy is one galaxy out of probably hundreds of billions. The distances between galaxies are far larger than the sizes of the galaxies themselves. For example, the size of the Milky Way, as I said multiple times, is 100,000 light years in diameter. Our closest major galactic neighbor, our next door neighbor, is the Andromeda Galaxy, which is about 2.5 million light years away. So we're talking about 100,000 light years compared to 2.5 million. This is a factor of 25. So the Andromeda Galaxy is farther, is about, not farther, the Andromeda Galaxy is about 25 times farther away than is the size of the Milky Way galaxy. That's a weird way of putting it, but in other words, imagine this is the Milky Way galaxy. This is the diameter of the galaxy. Take this diameter, multiply by 25. I'm not going to be able to do this to scale. It's something like this, possibly. This is the Milky Way. And then this would be the Andromeda galaxy. And this is our closest galactic neighbor. Okay, I think that you maybe get the point with that. I won't belabor the point any further. One thing I want to discuss with you is how we know how many stars are in the Milky Way galaxy. I told you around 100 billion. But what I didn't say is how we would know it's 100 billion versus 101 billion. You might think that we catalog stars in the Milky Way galaxy. You might think that we have telescopes and we study stars and then we can give them names or numbers. Indeed, we study stars, but there's no way to count 100 billion stars. You could just do a quick calculation. You could ask yourself how long it would take you to add up 100 billion of anything, stars or whatever else, if you counted once per second. And it turns out it's an absurd number of years. So there's no way that you can actually take a telescope and count the number of stars in the Milky Way galaxy. The reason we come up with the number 100 billion is because we use statistical measures to estimate the number of stars. And therefore we don't have an exact number. In fact, there's dispute about whether it's 100 billion or a trillion. So the number that people quote is not nearly as robust as you might think. There's new research on this, in other words, which suggests that there might be far more stars in the galaxy than we previously thought. I would like to go over with you in a separate video how you would go about doing this. How would you estimate using statistics the number of stars in the galaxy? I don't want to go through it in this video because it's interesting but not directly related to the main part of the material. So I'll post this video on Blackboard. This method that I'm going to explain to you is something that I made up, and it's not a very robust way of estimating the number of galaxies, but it does give you the right order of magnitude. It does give you 100 billion. The actual way we do this is more sophisticated, but this gives you a flavor for how one would do it. All right, let's skip this, since that's in another video. I encourage you to watch that video before you continue. So stop this, watch that video, and then let's continue with this slide. In this slide, I'm going to talk about different components of a galaxy. By components, I really mean maybe more like constituents. Those words are very similar, but in previous slides, I talked about some of the basic parts of the galaxy, such as the disk, the galactic center, etc. I would like to actually now talk about some smaller components. There are gas and dust clouds in galaxies. Some of these gas and dust clouds are what we call open clusters. An open cluster is a large cloud of, not large compared to a galaxy, but large compared to the solar system, a large cloud of gas and dust that is typically found in the arms of spiral galaxies that contains mostly young, hot stars. These are regions where star formation is occurring at a very high rate. We talked about star formation and solar system formation in previous lectures. So all of that is going on in open clusters. A good example of an open cluster would be the Pleiades, which to earthbound stargazers is known as, or is used to refer to, I should say, 7 easily visible stars in the constellation Taurus. There are 7 stars in that constellation that stargazers refer to as the Pleiades. These are also called the 7 sisters. And even though there are only 7 stars that stargazers refer to, the Pleiades actually contains probably 1,000 stars. And the reason for the discrepancy is that the vast majority of the stars you just can't see from Earth. I should say you can't see from Earth with normal telescopes that stargazers use. Because only 7 stars are really bright enough to be particularly visible. This is a picture of the Pleiades from NASA. Open clusters are characterized by having a lot of blue stars in particular, because they're regions where star formation is occurring. And that's because the regions where there's tons of gas and dust. That is the stuff from which stars form, as we know. So there's going to be a lot of hot young stars. In addition, there's going to be lots of gas and dust. These two things combined are a major clue that what you're looking at is an open cluster. Remember, these are components of galaxies. These are tiny components of galaxies. The Pleiades is one tiny segment of one spiral arm of the Milky Way. So galaxies contain huge numbers of these regions. A globular cluster, on the other hand, is a concentration of stars in the halo. The halo is the region that surrounds a galaxy that's mostly invisible. Not completely invisible, because halos contain these collections of mostly ancient stars. And that's what I was referring to earlier. Most of the matter in the galactic halo, actually most of the matter in a galaxy in general, is dark matter, the nature of which we will talk about later in this course. You may have heard of dark matter. It's a mysterious form of matter that is the subject of much speculation. But putting that aside, a good example of a globular cluster would be Messier 53, which is about 60,000 light years from the center of the Milky Way galaxy. And as I mentioned a little bit earlier, globular clusters contain typically old stars. These are old collections of stars, old relics, so to speak. These are not regions where there's tons of gas and dust. There is some gas, but generally when you look at globular clusters, you'll just see collections of stars with really no gas visible, and you'll tend to see older stars. These older stars, because they're old, will be metal poor. I'm going to get to the metallicity of stars a little bit later. For now, I just want you to put this in the back of your mind. We'll talk about which stars have more metals than others a bit later. Here is a picture of Messier 53. You can see that gas is not particularly visible in this photo. Really, you can just see collections of stars. It's a little bit hard to tell the colors of the stars. They generally look white, but you don't really see a lot of blue stars, although you do see some. These blue stars, by the way, are often called blue stragglers. These are atypically hot luminous stars that we do find in globular clusters. But hopefully, given my descriptions of these different regions, you can determine which is which from a picture. Let's move on now to interstellar matter, interstellar media. I talked a little bit about the interstellar medium when we talked about the formation of galaxies. The interstellar medium is the space which contains not just space but matter and radiation in between stars of a galaxy. If you were to traverse the stars, as you're going from one star to the other, you're passing through the interstellar medium. And this contains diffuse matter and radiation. In other words, it's mostly nothingness, but there's some particles and there's radiation. Let's talk about what exactly constitutes interstellar matter. It is constituted to the proportion of about 75% of hydrogen, about 23% helium, and then about 1% what we call interstellar dust, which is many tiny solid particles. You might be surprised to find out that many complex molecules have been found in the interstellar medium. Most of the interstellar medium, I want to emphasize, consists of just hydrogen and helium. This is a common theme. This is what stars are made out of. This is what nebulae are made out of. And if you look at the diffuse particles in the interstellar medium, you'll see exactly the same thing. And the reason for this ratio, about 75% hydrogen, 23% helium or so, is because of cosmology. We will get to cosmology later in the course. I keep saying that, I know, over and over, but when we get to cosmology, we'll learn that in the early universe, these are the only two elements that could have been produced in significant quantities. In any case, we find some surprisingly complex molecules in the interstellar medium. For example, we find water. The Earth is not the only place with water. Actually, we know that. I mentioned to you that Mars has water, although it's almost all in the form of frozen water. There's really no liquid water. Europa has tons of water that's actually liquid. And we find water in the interstellar medium. We find titanium dioxide. This is a molecule that's found in toothpaste as well as sunscreen. We find ozone, urea. Urea is excreted by biological organisms. I'm not saying that the urea in the interstellar medium is excreted by organisms. It can be produced by chemical processes, but nonetheless we find it. We find ethanol. We even find Buckminster fullerene, which is a complex molecule made of carbon. I want to skip most of this slide because most of it is extraneous information. There are different regions that we define based upon what they contain, whether they're neutral atoms or molecules. I don't want to bother with that. There's already too much information, so don't worry about this bullet point. I have a sort of extraneous piece of information here, which is glycoaldehyde has been detected near a protostar. That's just a simple sugar. Okay, that's just a factoid that's interesting to note, going along with complex molecules being found in somewhat surprising places. Organic compounds, therefore, are actually relatively common in space, at least more common than you would think. And there are some astrobiologists who think that Earth may have been seeded by these organic compounds early in its history, and that may have given rise to life. This is just an idea. Don't know if it's true, but it's a tantalizing idea, because if it's true, that means that in a sense we're the descendants of extraterrestrial organic molecules. Again, this is speculation. We don't know, but this goes along with the goal of astrobiology, the main goal, which is to find life outside of Earth. This is a depiction of the interstellar medium, not the interstellar medium, but just an example of it. And in this picture, we actually have an example of complex organic molecules that are often found in car exhaust and coal, etc., in space. I just thought this was a really neat picture, so I wanted to show it to you. Let's talk about what's at the center of the Milky Way galaxy. I actually mentioned this when we covered black holes. And so you won't be surprised to hear that at the center of the Milky Way galaxy, we think that there is a black hole. In fact, it's more than just think. We have really good evidence that there's a very large, what we call a supermassive black hole at the center of our Milky Way galaxy, which is referred to as Sagittarius A star. I mentioned to you that the mass of this black hole is equivalent to a few million times the mass of the sun. In particular, it has about 4 million times the mass of the sun. The first evidence of this black hole was found in 1974, but since then we've accrued tons of evidence for this black hole. This is a picture of the center of the Milky Way galaxy, Sagittarius A star. There's tons of stars in this region, so really this is just a picture of part of the center of the Milky Way galaxy. Let's talk about old and young stars. As I promised earlier, I will tell you which stars contain relatively large amounts of metals and which are metal poor. We divide excuse me, we divide stars into three populations. We have multiple ways, as you now realize, of categorizing stars. The main way is via the O through M classification scale, which is really a temperature scale. But we have this way as well of categorizing stars, which is based on their age. Population 1 stars are relatively young. These are rich in metals. These stars are rich in metals. And the reason they're rich in metals is because they actually formed from the, I don't want to sound too morbid here, but the excreted gaseous guts of long dead stars. It's a sort of poetic way, but also macabre way of putting it. The idea is that stars that are very large and hot burn their hydrogen very quickly. I mentioned that to you when we went over stellar formation and evolution. In fact, truly massive stars may only live 10 million years or even a few million years. They will exhaust all of their hydrogen in the core, not in the rest of the star, but that's the only place where hydrogen can be fused. And then they become red giants, and then they start to fuse helium, and they get up to iron, and then they explode. When they explode, they emit their gaseous guts, so to speak, throughout the region, and these gases will go on to produce other stars. Therefore, the sun, for example, is actually, and the whole solar system in which we live, is actually the progeny, it's the child, if you like, and the great-grandchild, etc., of many generations of long dead stars. This explains why we have some really heavy elements on Earth, for instance. We have elements such as iridium, uranium, etc. These are pretty rare, but they are still on Earth. And the reason they're on Earth is because they were produced from supernovae that occurred billions of years ago, when huge stars formed and died and exploded in supernovae. And I mentioned to you when we talked about the deaths of stars that elements heavier than iron can only be produced in these massive stellar explosions called supernovae. So that's where these heavy elements come from. They don't come from the sun. In fact, none of the elements we have on Earth come from the sun. Hydrogen and helium that we have on Earth come from the cloud of gas and dust that formed the solar system, and the sun is also composed of hydrogen and helium. But that cloud of gas and dust also contained oxygen, carbon, etc., all these things that we need for life, for example. And the elements that are the elements other than hydrogen and helium that are less massive than iron, or as massive or less than iron, came from nuclear fusion that occurred in the cores of stars that lived and died. So in other words, all the elements that are heavier than helium all the way up to iron, they're produced in the cores of stars during normal fusion. Elements heavier than iron are produced in explosions of stars, supernovae. This explains why the sun has metals. The sun does not produce metal. The sun is relatively rich in metal. By rich in metal, I mean relative to other stars. It doesn't mean that most of the material in the sun is metal. Metals constitute a really tiny proportion. But relative to other stars, the sun is rich in metals. These metals, such as iron, literally, or other metals, come from, as I have said several times here, sorry to repeat myself, but previous generations of long dead stars. Okay, I'm belaboring the point, but let's go on to population 2 and 3. Population 2 stars are relatively older. These are almost devoid of metals. The sun is a population 1 star. And then we have population 3 stars, which are the oldest stars, and they are completely devoid of metals. These were thought to be purely hypothetical. And in my slide here, I say they are purely hypothetical, but very recently, astronomers believe that they've been discovered. I'm going to post a video on Blackboard that I want you to now watch. This video is slightly antiquated, but I'm going to put some information about recent evidence for population 3 stars. So in any case, I hope it's clear now why some stars have more metals than others. It's really a consequence of how young or old they are and not how many metals they produce. Maybe I need to connect the dots just a little bit more. How come stars that are very old have very little metal? Because they are the progeny of very few generations. If a star is 10 billion years old, it cannot be the result of many of these generations of stars that lived and died. Whereas stars that are just forming today are going to be the results. They're forming literally out of the gases that came from many generations of long dead stars. And so there's been more time for metal to build up. That's the point. The very first stars that formed had no metals at all because there were no metals in the universe. Metals can only form inside stars, and the very first stars, therefore, did not have any metals. All right, hopefully that's clear. I want you to watch this video, and when you're done, come back to this slide. The last thing I want to do in this video is go over galactic classification. We've done a lot of classifying in this course. We've classified stars, and now we're going to classify galaxies. This is one thing astronomers like to do. Scientists in general like to classify things. As you know, if you've taken biology and chemistry, etc. Let's talk about spiral galaxies first. That's the first kind of galaxy I mentioned to you. We live in a spiral galaxy, the Milky Way. Our closest major galactic neighbor is the spiral galaxy. Spiral galaxies come in 3 basic forms: SA, SB, and SC. And these three types of galaxies essentially practically speaking, refer to how many obvious spiral arms a galaxy has. In practice, SC galaxies tend to have more obvious spiral arms than SA types. A classic SA galaxy would have 2 very clear spiral arms. Classic SC galaxies would have many spiral arms, although the spiral arm structure tends to be very loose, so sometimes it's hard to count how many arms an SC galaxy has. More precisely, these classifications really have to do with the tightness or looseness, among other things, the tightness or looseness of the arms. It's not really about how many arms the galaxies have, but in practice, it's usually about that. SA galaxies tend to have very tightly wrapped arms, and SC galaxies tend to have very loose, poorly defined arms. As I said, in practice, that really means that SC galaxies will look like they have many arms, and in fact, it's often hard to count how many they have. I want to show you some pictures to try to illustrate this. This is a classic SC galaxy. You can see here that there's clearly more than 2 arms, although it's hard to count, as I keep saying, how many there are. Something like this. This is an SA galaxy. This galaxy has spiral arms that are rather well defined, and there's rather obviously just 2. As I said, this is not always the case for SA and SC galaxies. They don't always look like these stereotypes. I'm stereotyping the galaxies a little bit. You'll see SC galaxies and SA that look different, but for the most part, these are the characteristics of the galaxies. Hopefully now you'll be able to differentiate these. SB galaxies are in between. Let's now look at S0 galaxies. These are also called lenticular galaxies. These are spiral galaxies that don't have arms. In other words, they're just galactic bulges, galactic centers. I will show you a depiction. I think I have a lenticular galaxy. Yes, here is a lenticular galaxy. You can see the galactic bulge, but there are no arms. Next, we have elliptical galaxies. These are oblong shaped. They are elliptical. Remember, I mentioned that planets orbit the sun and stars in general in ellipses. These are ovals. They're like circles that are stretched out. We have galaxies that roughly look like this as well. There's no connections, just the basic geometric shape happens to be similar. These are oblong-shaped galaxies that contain few young stars, and we actually categorize them from relatively spherical to relatively elliptical. I think I have an example of an elliptical galaxy. Sorry, that's not it. Here it is. This is an elliptical galaxy. This is an E3 galaxy. E7 being highly elliptical. This is roughly in the middle, so it's an E3. Finally, we have irregular galaxies. This is a category for any galaxy that doesn't fit the other types. I put this in a somewhat poetic way. They lack any semblance of a well-defined geometric shape. These are galaxies that literally look irregular. They have all kinds of very interesting, often beautiful shapes. Just because they don't fit into a category doesn't mean they don't have beautiful shapes. So this is an irregular galaxy here. This is another irregular galaxy. This is a ring galaxy. I don't want to go into that. I'm sorry, there's not quite enough time to go into all these little details, but this is a peculiar galaxy called an antenna galaxy, or actually it's pluralized. These are the antennae galaxies, or antenna galaxies. I have other pictures here. I don't have time to go through each one, but feel free to look through them in the slides that I will post to Blackboard. So these are the different types of galaxies. They are neatly cataloged in this figure that I took from NASA and the European Space Agency. We have the elliptical galaxies on the left side. Remember, E0 are highly spherical and E7 are highly oblong. Then we have the lenticular galaxies, which are like spiral galaxies without the arms. These are basically just galactic bulges without spiral arms. Then we have the three main types of spiral galaxies, SA, SB, and SC. The practical difference is usually that SA galaxies have two clearly defined arms, whereas SC galaxies have many arms that are often hard to count because the spiral structure is not very clear. We also have barred galaxies. I mentioned this at the very beginning of the lecture. A barred galaxy is just a barred spiral galaxy, is just a spiral galaxy that has a bar-like galactic bulge. It literally looks like a bar. So that's it. And then we can categorize barred spiral galaxies as A, B, or C. I think I have a picture of a barred spiral galaxy somewhere. Perhaps not. Okay, I may have taken it out. In any case, you can Google barred spiral galaxy. I apologize for not having a picture, but as I said, this is a tangential part of this lecture, so don't worry about the barred part. I just want you to have seen this. Very finally, let's talk about other galactic-like objects that are exotic. These are quasars and blazars. These are extremely luminous compact objects. Excuse me, I'm having trouble speaking today. These formed roughly around 12 billion years ago. They can be up to 100 times as luminous as the Milky Way galaxy. And they seem to consist of very dense visible matter surrounded by a supermassive black hole. A blazar is the same thing. It's a quasar which emits radiation in the form of a jet. This is a quasar, and this is a picture. These are real pictures. This is a picture of a blazar. Most of these objects are very far away, and they give us insight into what was happening in the universe many billions of years ago. There's a lot more to be said about that, as most other things, but sadly, this video is already long enough. Thank you for watching this video on galaxies, including our Milky Way. We talked about the basic components of galaxies in terms of their overall structure, but also in terms of some of the different types of gas and dust clouds that exist within them. We talked about the different ages of stars, the 3 different populations of stars. We talked about the sizes of galaxies and how we estimate, well, that's for another video, but I mentioned to you that we estimate using statistical techniques the number of stars in galaxies. And then finally, we learned how to classify galaxies based on their shapes. Once again, thank you for watching this video, and I will talk to you in another one.